Hello, my name is Zachary Chenoweth, and this is my presentation for Lab 2, Task 1, Motion with PID for Control of Mobile Robots. Now for this task, we are required to have our epoch robot traverse this corridor and stop about 10 inches from this front end wall, also while staying away from the side walls. Now in order to accomplish this, we use something called PID, which stands for Proportional Integral Derivative. It's basically a way to proportionally calculate a velocity based off of the distance sensors of our epoch robot. Now this epoch that we are using has 3 distance sensors. We have a front distance sensor, a left and a right distance sensor, which the max distance for each of these is about 50 inches. Here in our controller, we have our initial setup of the robot. So this sets up our distance sensors, our position, and the robot's motors, as well as the timestamp for the program. Here we have some constants that we need. Our Cmax and our Cmin are basically the minimum and maximum velocities of the robot in inches per second. So basically, the robot can't go faster than 5.024 inches forward or negative 5.024 inches backwards. Our Kp values here are the proportional gains we're going to use in our calculations for the PID. Kp1 is the proportional gain we're going to use when calculating the front distance from the wall. And the Kp2 is going to be for the sidewalls. Our RT values are going to be the desired distances from the front wall and the side walls, respectively. So we want our robot to stop about 10 inches from the front wall, and we want ideally for our robot to be 3.86 inches from the side walls. Now, because of the width of the corridor, it's not going to be exactly 3.86 inches. So what we'll see the robot actually kind of zigzag its way through the corridor as it's adjusting itself. And here we have the time we want our program to end. We ideally want our robot to finish its movement in about 30 seconds. Our first function here is our F saturation function. This is used in our PID calculation, and what it basically does is it prevents the robot from exceeding the maximum or minimum velocities. For example, if we calculated a velocity of about 6 inches per second, that's greater than our maximum velocity, which is 5.024 inches per second. So this F saturation function will return 5.024. If it's between those values, then we return the calculated value that we got. And if it's less than Cmin, then we want to return Cmin, which is negative 5.024. Here we have our forward velocity function. This is going to use just the P in PID, so the proportional component of the PID. And this calculates the forward velocity for our robots. Here we have the current distance. We read the front distance sensor, and since the front distance sensor reads in meters, we have to multiply by 39.37 in order to get it to inches. Here we have our error. So the error is just the desired distance minus the current distance the robot is reading from the front distance sensor. Now, because the front distance sensor's max value is about 50 inches and we only want it to go about 10 inches from the front wall, there are going to be situations where this current distance is going to be much larger than our desired distance, so the error value will become negative. In order to account for this, we basically have this if statement here saying if our error is negative, meaning the current distance from the wall is larger than our desired distance. So like in our initial state, the 10-inch mark is about where this line is. So our robot is going to read a distance that is much larger than our desired distance, making it negative. In order for the calculations to be right, we're going to take the absolute value of the error and set our error to that absolute value. Else, if our RT is bigger than our current distance, meaning that the robot is actually closer to the wall than what we want, then we want to make our value negative, so that way the robot will go backwards rather than forwards. Here we calculate the velocity by multiplying our error with our proportional gain, Kp1. The proportional gains can change, and we can set it to whatever value we want. We just have to take into account that the higher the Kp value, the more overshoot we're going to have. So meaning, like for example, if we're zigzagging between these sidewalls, making sure it's not going to hit the wall, when it's reading the sidewall, it's going to multiply by a bigger number, forcing it further, like to go away from the wall faster. Same thing with the front distance sensor. So if it gets too close to the front wall, it's going to drive away from that wall faster, but it might have some overshoot, so the values might not be as exact. Our URT is going to call our F saturation function that I showed earlier. So this basically makes sure that we're setting our motors to velocities that does not exceed our minimum or maximum velocity. And then finally, we're going to convert our calculated velocity to radians per second, because in Weebots, the motors are set using radians per second, not inches per second. And then finally, we're going to send our values into the left and right wheel functions in order to calculate what the velocity of the wheels should be in order to stay away from the walls. Here we have our left wheel function, and this is going to use the P component of PID in order to calculate the velocity of the left wheel. Now, this calculation is somewhat similar to the forward velocity with some changes. Here again, we have an error where we take our desired distance from the sidewalls, which was 3.86 inches, and then we subtract the opposite distance sensor. So for this function is based off of the left wheel, we're reading the right distance sensor. Now the reason we do that is because if the robot is getting too close to this right wall, we want to stop the left wheel or slow it down in order for the robot to drive away from that wall. And that's why we use the opposite distance sensor. Here we have if our error is negative, meaning the distance sensor, the value of the distance sensor that we're reading is larger, meaning that it's closer to the left wall, then we want to keep the calculated velocity. So we want the left wheel to be going as fast as possible in order to drive away from this wall. Or if we get close to our goal, which was the 10 inches per second, then we want to stop it from adjusting based off of the sidewalls, because when the robot gets to this position here, it's going to try and stabilize at about 10 inches, and it's going to constantly adjust for the sidewalls. So you'll see the robot slowly turn in place. And then after a certain distance, it's going to say, oh, well, these distance sensors are reading a larger value now because of how it's angled, and it'll start driving forward or backwards or whatever the robot is reading. So we want to make sure that we adjust for that. Else, if our calculated velocity is a negative number, meaning that we want it to go backwards because it's too close to this front wall, then we want to take that velocity and add our error times the second KP value in order to reduce that number, because if this number is negative and we subtract the error, then it's going to make this number larger than our minimum velocity, which was negative 5.024. And we can't have that because it'll cause errors. So we want to add to that number. Else, if our calculated velocity is positive, then we want to subtract this error times the KP value to reduce the speed, again, for the same reason, because if this was an addition, then it would exceed the Cmax velocity, which is 5.024 inches. And again, it'll cause errors if we do that. Once this calculation is done, then we set our left motor to our URT value. Our right wheel function is going to function exactly as the left wheel one does, except for the fact that we're going to read from the left distance sensor this time. Again, we calculate the error. We check if the error is negative or if the current distance is equal to 10. And we set our velocity to the calculated distance in those cases. Otherwise, we're going to add and or subtract the error times the KP value based off of if the calculated velocity is positive or negative. And then we're going to set our velocity here to these calculated values. Here's our main loop where we're reading the time that has passed since the simulation has started in order to stop our program once it hits that 30-second mark. We have the current readings of our distance sensors, the front, left, and right, respectively, and we're printing those values with 4 decimal precision. Here we have an if statement where it says if time passed is less than 30 seconds, then we want to move our robot. Otherwise, if the time passed is greater than or equal to 30 seconds, then we want to stop our robot where it's at and then end the program. So that's the basic controller. Now let's go ahead and see the robot run. So as you can see, as the robot's running, it's adjusting itself from the sidewall, so it's kind of zigzagging. And then once it gets to about the 10-inch mark, it's going to stabilize at about 10 inches. Now, if I decide I wanted to move the robot back while it's running, you can see that it's going to kick in again and it's going to readjust back to this position. Same thing if I decide to move the robot forward, it moves back to this original position and then stabilizes. And then once the program hits 30 seconds, it's going to end. And that is all this presentation has. So once again, this is Zachary Chenoweth presenting Lab 2, Task 1, Motion with PID for Control of Mobile Robots. Thank you and have a nice day.